Welcome everybody. So let's turbocharge our tooling today. We're going to go from CAD to first shot in days and not weeks. That's the topic of this webinar in partnership with BASF Forward AM. So this is a really exciting webinar topic because it really converges 3D printing with traditional manufacturing, which is pretty exciting. By the end of this webinar, we're hoping that you'll have learned how you can reduce your cost and accelerate production times using ultra-fast 3D printing tooling solutions. And we're excited to gain some valuable insights from industry leaders at BASF Forward AM. So let's go ahead and meet those experts. I'm Tyler. I'm hosting the webinar. I'm going to handle all of your Q&A questions. So if you have questions throughout the webinar, please make sure to post them in the Zoom section at the bottom, and I'll be happy to answer those. I'm actually here in Ventura, California, where our headquarters is based at. And I'd love to know where you guys are all signing in from. Please post those up in the comments and we'll give you a shout out. I'm also here with Robert Liba. Robert is a AM applications engineer for BASF Forward AM. And Robert, you're in Germany, is that right?
That's right. Thanks, Tyler. It's good to be here. Based in Heidelberg.
Awesome. Thanks for being here today with us. You've been with BASF Forward AM for about 7.5 years, and you have been hands-on developing parts using additive manufacturing methods and materials for BASF AM Forward. So before we dive into the webinar and get into like the meat and potatoes of this experience, we're going to learn a little bit about Nexa 3D in case you haven't heard about them. We were founded in 2016. Again, we're headquartered in Ventura, California. We have worldwide distribution through many resellers throughout the world. And we have an extensive product line that spans from resin 3D printing to laser sintering. And then now we just brought in filament with the acquisition of Essentium. We have 40 plus validated materials, and with more on the way with the filaments coming. But we're also an open material platform. So if you want, our NextX software is capable of handling your own validations if you want to bring other materials on board. For the purpose of this webinar, we're going to talk about just our resin 3D printers lineup. We have our Zip Pro, which is the newest to a resin printer line. And then NXC 400 Pro, and then the mighty Zip Desktop 3D printer. So if you want to learn more about our resin 3D printers, feel free to scan that QR code on the right, and that'll take you to more information about those technologies. And our resin 3D printers are backed by our lubricant sublayer photo curing technology, LSPC for short, much easier to say. And that's basically what makes the our 3D printers ultra fast and incredibly efficient. So 20 times faster than traditional LSA and DLP technologies. They're uniform, distortion-free illumination, self-lubricated everlast membrane, and it ties into NextX software as well. So the whole process and ecosystem works together. And at the end result, you get excellent surface finish really fast. And you can get really technical if you download the technical guide at the bottom. If you scan that one, that will give you a very good overview of what LSPC technology is. So these are kind of the people. These are the people that use our technology. Don't have to name all of them, but we're in really good company. And they all have a common need for speed. So that's a little bit about us, a quick nutshell. Let's get into while we're all here, which is 3D printed tooling. And so I'm going to give it over to Robert.
Okay, should be all set. So let's talk about this application of resin printing, turbocharge your tooling from CAD to first shot in days and not weeks. Over the past, I would say 2 years, we put quite some effort into developing a new resin specifically for this use case, specifically for printing mold inserts for injection molding. But this is not the only use case I'm going to talk about today. But before I jump into it, let me give a quick introduction of our company. So we are BASF Forward AM based in Germany, and we mainly develop and sell materials for all kinds of 3D printing technologies. So we do filaments, we do resins, and we also do powders, all in plastic, except for two metal filaments, which we have. And they are basically plastic filaments, but filled with 80% metal powder. And after a sintering stage, you get actual metal parts from any 300 euro FFF printer. But along with these materials that we develop and sell, we also support customers with consultancy. We support with engineering services, means CAD work. We can do FE simulations. We do quick prototyping to iterate designs and do functional improvements. And we also develop or work with partners to improve the finish of the parts, which means we have coatings in different colors. They are also flexible. So for our flexible materials, these coatings will not rip. They will make the same elongation and stay nice. And as I said, if customers want to use our products to make their own products, to make parts, feel free to contact us. We are here to help. So we have sites worldwide. We have the headquarters here in Germany, Heidelberg, with roughly 100 people. We have in the Netherlands is the filament production. In Paris, we have acquired Sculpteo, a service bureau, already some years ago. In Frontonas in France as well is the powder development and production. And then we have also application experts and application technology centers to validate materials and to make customer parts and samples in Shanghai, smaller team, and also in Detroit, USA, with a little bit bigger team of 18 people. So the topics for today I want to talk about are, for one, the ceramic filled X-ceramic 3280. We call it RG3280. So if I mix up the names, please don't be confused. It's the same. This was specifically designed for printing injection molding inserts. And the second material or second topic is X Pro 1100 Black, or we call it RG 1100 Black, which is better suited for printing polyurethane molds. In this case, the example is a midsole or shoe sole mold. So let me start with showing a video of the injection molding topic. When we started looking into this, doing investigations, we needed a partner, and we found them with SKZ, a German injection processing or plastics processing institute. They had a reference, a benchmark mold design, which we just adapted a little bit for 3D printing, printed this insert with RG3280. These are the white parts you can see here. Mounted them into the base mold, onto the injection molding machine, and off we went with the trials. By slowly increasing temperature and pressure, so starting carefully and then ramping up those parameters, we were able to make nice parts and also evaluate by looking at the benchmarking mold geometry, what is possible and what not. So we had different kinds of rib sizes, different draft angles, and different features overall to validate this. And we found it works quite well, even compared to the market competition. And But to be honest, it's not straightforward. It won't work just right out of the box. If you do it right, we have extensive guidelines for this. You can be successful. So the 3D printing really makes sense to use for rapid tooling. These are some of the market demands we see. The faster time to market is what we hear from everyone in the industry. This would give a big advantage over the competition. So here 3D printing really helps. 3D printing also helps to optimize the supply chain. So also a big buzzword is sustainability. So you can actually produce close to where the part is needed. You can save on some of the shipping costs and logistics. And also you have the advantage of having a digital inventory, which means you can develop your part or everything around the requirements on one side and then send everything over to the production side, which can be close to where the parts are actually needed and produced locally. So let's have a closer look at the material itself, ceramic 30-80. So it is a ceramic filled urethane acrylate resin, and it especially excels in its high stiffness of 10 gigapascals and its high temperature resistance, where we are speaking about an HDT of 280 Celsius. So this means for most of the plastic injection processes, this material should be able to hold up. It is a low viscosity resin, so it prints quite easily and fast. The high amount of ceramic particles in there are very stable. So you just shake it or roll the bottle before you start the printing process and you're good to go. You will not see differences in the particle distribution. It's very stable, as I said. It comes with one drawback though, and that is the elongation at break. So it is a rather brittle material. Though being strong and stiff, try not to drop the parts. They quite easily break. And keep that also in mind when you design molds. I will come to this topic in a minute. So some trends where printed mold inserts really make sense. As we already saw, the faster time to market, by printing inserts, you can skip the CNC milling and save a lot of time, especially in the early stages of a new part or development or of a new mold or tool development. It also makes sense if you only have a smaller quantity to produce, and it's just not worth to invest in one of the bigger, more costly metal-made molds. And another point where it makes sense is if the mold design is especially complex and you reach the limit of simulation capabilities. So before you invest in a complex metal mold and are not sure if the process is going to work, you can print a mold insert and validate the process. And all of this can happen, the 3D printing, the post-processing, the preparation for injection molding, and then doing your first shots. All of this can happen in 2 to 3 days if you do it yourself on site, versus the more common duration when you order aluminum or steel molds of roughly 1 to 2 months, or sometimes even longer. So of course, there's a limit to this technology. Most printers are only give a certain build platform size, but not only this limits the build size or the mold size that you can print, but also the physics. So we are printing plastic here, so you will see a certain amount of warpage, and we we saw that up to a size of roughly 150 millimeters, you are in a range where you can control the warpage quite well. Over this, and it gets more complicated. It's still possible, but you will need to do you will need to have some tricks up your sleeve. It also makes sense when you want to develop a tool, and in this early development stage, you want to test some of these tool features. You want to do some first shots to see if your injection molding simulation is right, and this kind of development stuff. It also is really useful during the product development. So for example, the final product, the final mass-produced product needs to be in a certain plastic, a certain material which is not available on any 3D printing technology, but you need it for validation, for testing. By printing injection molding inserts, you can use this later mass production material to get first samples for your testing phase. And also it makes sense for small batches where it's just cheaper and faster to print the mold inserts instead of traditionally manufacture metal molds. So let's look a bit closer at the process itself. As I said, it's not a you push the button and the printed mold will work perfectly. You will need to do it right, but we're here to guide you through this. So the material itself is optimized for the DLP process, which Nexa machines, of course, use. We recommend to orient the mold inserts in a way that the parting line or the parting surface is parallel to the build platform. It will give you the best surface quality in this region. We also recommend to lift the part up a little bit above the platform. It's not necessary, but especially this rigid material can stick to the build platform quite an amount. And this way you will have it much easier to remove it from the build platform and continue with the process. On the printing itself, you can see quite some numbers here about exposure times that we recommend and layer exposure times. You can find all these numbers in our guidelines. I will provide a link or QR code later where you can download these. Also here we have parameters ready for you to print in the best possible quality for this application. After printing, the cleaning step is necessary, and here diligence really will save you from troubles later. For example, really fine holes. Due to the capillary effect, you will have some resin, some liquid resin still being stuck in there. So be sure to poke it out in this stage, because right after the printing and cleaning stage, you will put the parts into a UV curing station, and every resin residues will harden during this UV curing. And if holes are clogged with liquid resin, they will fully be blocked after the UV curing stage. So here, this is the UV curing stage. So cleaning and UV curing are quite quick. It really doesn't take long to reach the final technical data sheet values for mechanical properties. However, the UV curing stations, so we are a material developer. Our materials run on multiple machines, and we cannot be sure what curing station the customer or the user really uses. And also here you see some slight differences from printer to printer and curing station to curing station. And to mitigate these differences, a thermal treatment can help. It's not necessary, but it really helps to get to these final mechanical properties, especially for the thermal resistance, the HDT value. It helps you to get out these last 30 degrees Celsius. So for, let's say, for easier plastics with a lower melt temperature, speaking of the injected plastic, it's not necessary to thermally cure your printed parts. but for the more demanding materials, we recommend it. Final step then, also not always necessary, but we saw a big increase in the ease of part release, is spraying the cured parts with your release agent and baking it for a couple of hours at roughly 60 degrees Celsius. So as I said, the material is rather on the brittle side. So you really want to make sure your printed mold insert is not warped. It does not stick out of the base mold, or is in any way dimensionally too inaccurate. So a quick machining of the backside can already erase most of the problems we see. Because when the two mold halves are not aligned properly and the injection molding machine closes, these printed inserts will crack. So milling the backside flat will reduce this problem already by a lot. We did a lot of machinability tests. This is just one video I want to quickly show you. I hope it starts. You should be able to see that even with a complex structure like this, with this gyroid structure, milling is no problem. You might get a little bit of chipping here and there, but for functionality, that is not a problem at all. The video does not want to start. Okay. Excuse me. Seems PowerPoint just froze. I'm really sorry about that.
No problem. Technical things happen all the time.
All right, quickly restart. Go through it again. Good old Microsoft Office. Okay, here we go. So let's see, second time's the charm. Yeah, here we go. So yeah, just to give you a visual impression of what this could look like. This is no special mill. It's a really simple top mill with a 10 millimeter diameter mill bit in here. We also have a guideline on this available. I think it's almost finished. It should be put online within the next week, I think, giving you RPMs and feed rates for milling this material. So here you can see some of the injected plastics we have tested so far. By now, the list is much longer, but these are some good representatives for unfilled and also for fiber-filled plastics, where we were able to get good results. So whether it's an ABS, POM, or a polycarbonate, you will be able to get good parts out of the printed mold inserts. But not even these unfilled materials, also more demanding fiber-filled plastics, like even a PBT GF30, we were able to get good parts. I will have a use case of a customer in a couple of minutes showing PBT GF20, which they use to develop their mold and their products. I want to mention the easier materials, the easier plastics without fibers, you will be able to have a higher yield, get way more parts out of there before you will see first cracks in the mold or first corners chipping off. And I'm speaking about 1,000 to 2,000 parts, which is possible. For the fiber filled, especially the highest demanding, like a PBT GF30, you will be able to get more in the ballpark of 20, 30, 50 good parts, maximum 50, I would say. Really good parts, because the first 10 to 20 parts are used to find the right filling parameters of the injection molding process. So and we go a little bit beyond just testing out if it works or not. We did an investigation on the thermal properties of this material, and we created a material card for mold flow, which is a common injection molding simulation software which simulates the injection process itself. And there it's now possible to then select RG3280 or X-ceramic 3280 as mold material and run your injection simulation. And we found that also the results of the simulation, they are within plus minus 0.5 seconds of what we found as the optimized process cycle time during our trials with SKZ. So it is a ceramic filled plastic, which also means thermal conductivity is lower. And we're speaking about roughly 1.5 times longer cycle time than in tool steel and roughly 3 times longer cycle time than in aluminium. But again, if you only do a prototype run of 50 parts or even 1,000 parts, usually that's not the critical criteria. All right, so here's one of the use cases we did ourselves, so we are free to share. This is a little phone holder, the part you can see in the picture on the right. The mold insert is a 2-cavity mold, so 2 parts with 1 shot come out. It is a PBT with 10% glass fiber. And we really wanted to push the limit. So we wanted to see if we can run it in a fully automatic mode on the injection molding machine. And after the initial setup phase, we were able to run a full shift of 8 hours and produce over 400 parts with 1 set of mold inserts. And they still look good afterwards, so we could have made more. But let me walk you through the process. So the tooling design time is, of course, it's a rather simple mold insert, is roughly 2 hours for the first iteration. We then saw some burn marks from the diesel effect in the corner of the part and had to do a second iteration, which means just adding ventilation channels. So within roughly 3 hours, we had finished the mold design. The print time on the fast printers of Nexa was roughly 1 hour for the entire mold insert. The post-curing and cleaning comes to about 20 minutes, and the thermal post-curing to 420 minutes in an oven. But as I said, it's optional. If the injected plastic you want to use is on the less demanding side, you can also leave it out and save the time. After the thermal curing, we did machine the printed inserts, which is roughly 1 hour. So from start to the final ready machined mold insert, it took roughly 12 hours. And then from there, putting it onto the machine, doing the first shots and letting it run for the rest of the shift. So within a total time of roughly 20 hours, we had 400 parts ready to use. The second case study is from a customer of ours, from MD Electronic. They are a tier 1 automotive supplier for all the major automotive brands, mainly in Germany, but also worldwide. They use it for, here in this use case, to validate the injection process itself. So their main business is making cables and also connectors for data transmission cables. And here, automotive grade plastics are not available on any 3D printer. So in the development phase, they need samples out of this material. And since In this case, they have flexible inserts, so a cable and also PCB boards go into the mold. The mold is then closed and plastic injected, which then flows around these inserts, these inserted parts. And MD Electronics says that's the point where simulation software comes to its limits, especially with these flexible inserts. It's not possible to simulate this. So to be sure that the layout of their filling strategy works also in the mass production mold, in order to validate this, they print smaller mold inserts and do the testing. So on day one, it's all about the design of the part itself, and then making small modifications for 3D printing. Same thing goes for the to be printed mold insert. Once the design is finished, they go to their rapid prototyping center and print the mold inserts. And by printing these molds vertically, they're able to fit more on one build platform and have a higher yield. In this case, it's a special case. It's okay to print vertically because there are no critical overhangs in the cavity. Once you have bigger overhangs, you will need support structures to make it printable. And support structures mean that your surface quality will go down. But here in this case, it's only small overhangs, which can be printed support-free. So once the prints are done, it's time for the post-processing. According to our guidelines, these finished mold inserts then go into the injection molding machine, into the base mold, and the process starts with a slow cycle and low pressure, which is then step by step ramped up to get to a good result. And all of this can happen within 2 to 3 days. So summarizing again this use case, as I said, the design of the part itself was modified a little bit to accommodate for the 3D printing process. It was especially useful for the because these types of overmolding processes cannot be simulated. There are integrated electronics. That's also a reason why they need the serial production plastic, because there's it will strongly influence how the electronics work. With these prototypes, they can also run the tests on adhesion and tightness of the cable, and also test the fitting of the clip mechanism. They not only tested our material, the RG3280, but they also benchmarked it against the industry standards, or let's say the state-of-the-art material at that time, before our material came. And conclusion was our material performed the best, which means the edge sharpness or the edge resolution was the best on the printed mold inserts, and then accordingly the molded parts. But also the amount of parts they were able to get out was the best with our material. So in this case, they were able to get over a little bit over 60 good parts made from PBT GF20 within 90 minutes. Our marketing team put together a nice video about this use case. I want to show it to you.
MD Electronic is an automotive supplier. We are producing data transmission cables for the automotive industry. More than 60 OEMs worldwide rely on AMD products. In Europe, we are working with the traditional OEMs from Germany, which is Volkswagen, BMW, Porsche and Mercedes. International as well, we are working with Ford, with General Motors, with Tesla. Over the last 10 years, more and more electronic systems came to the cars. And so we see nowadays more and more data transmission lines within the car.
I'm Markus Kaserer and I'm expert techno polymers at AMD Electronics R&D department. At our cable connectors we often have overmoldings. Overmolding is when we inject plastic material in a metal mold over a cable. We use the injection molding simulation to find out the right design for our connectors and also for the mold itself. The problem with the injection molding simulation is that it comes to its limits when we have something like flexible inserts in our cable connector housings, which cannot show the real behavior of the filling of the mold. The molds which we use for the production of these parts are made out of metal. To build this mold, it takes a lot of time, for example 12 or even 20 weeks, and of course they are also expensive. As these iteration cycles are always very time consuming, we try to find a solution to accelerate this process.
When AMD Electronic came to production to go, we were looking through many different materials tests, and what we found out is it's actually the ceramic 3280. The ceramic 3280 is perfect for injection molding and inserts, mainly because it can take a certain amount of beating and also an amount of temperature. When combined with the NXC400 from Nexa, you're able to actually create the perfect fusion of two technologies to create parts that are not just dependable, reliable, but also actually very durable.
With 3280 material, I had the best and finest details so that we could apply high pressure without overfilling of the mold. Now that we found out that this is a capable solution for us, we can cut down the iteration cycles in the metal mold and speed up our development process.
Injection molding is actually a very old technology. But what's quite interesting is when it's combined with 3D printing, you're actually able to create things outside the norm.
Thanks to this solution, we can reduce the iteration cycle in the steel mold and get faster time to market.
Nowadays it is required to have a fast solution for new data connectors. So we use the additive manufacturing technologies for providing early samples to our customers and to the engineering lab, which brings us in a better position than the competitors.
All right, nice video. Okay, so for everyone who's really interested in this solution and trying it out yourself, we have a broad variety of supporting documents to get you started. We have a user guideline explaining the printing of the material itself. There's an extended TDS with all the relevant information about the mechanical properties, thermal properties, chemical resistance, about the material itself. We have the mold flow simulation guideline, the injection molding processing guideline, and we, together with a partner, we also made a white paper going deeper into this benchmarking trial at SKZ with all the different features, rib sizes, ejector pin holes, and draft angles and whatnot. And on BASF sites, you will also find extensive guides on troubleshooting for the injection molding process itself. We have prepared a landing page where you can download all of these documents. So I will leave this QR code for you to scan for a couple of seconds, maybe half a minute or so. So you can go to the page and download everything. and more and more documents will be added. What was missing in the list you just saw is the guide for the machining. It's still in preparation to be uploaded to our webpage, but I think it should have been finished this week. If not, I will speak with my marketing people again. But should be there very soon. All right, I will continue. And yeah, that's about it for this first use case of using Ceramic 3280 for printed injection mold inserts. The second material and second use case I want to talk about is the X-Pro 1100 Black, and we found it to be especially useful for foaming molds. In this case, polyurethane molds. So the HDT, the temperature performance is lower than the ceramic filled of the ceramic filled material. Also, strength and stiffness are lower, but foams don't require these high properties, and so we can go with a more affordable material, which in this case is the X-Pro 1100 Black. So the material itself is validated rather newly on the Nexa machines, but it's a low viscosity material which prints really well. The stiffness, the Young's modulus is 2,950 megapascals. The tensile strength is about 70 megapascals, and the HDT here is around 100 C. So as I said, much lower than the ceramic filled, but for the biggest part of foams, this 100 degrees Celsius of temperature resistance is enough. It also excels in a really low water absorption and a really high chemical resistance. Chemical resistance, especially in the context of molds, is important because there are many aggressive cleaning agents and release agents which come into contact with the mold surface. So we determine the chemical resistance of our materials by printing tensile bars, in this case of the type ASTM-D638, type 4 tensile bars, and then just letting these tensile bars sit in these chemicals for either 30 minutes or in some cases up to 7 days. All of this information is also in the extended data sheets for this material. But in the diagram that you can see on the right, it's the data from the 30 minutes tests. And as you can see, compared to the control, which is on the far left side, which means tensile bars without any chemical contact, that the material does not deteriorate much. So E modulus and also the tensile strength and also elongation at break go down a little bit in some cases, but usually not below 80% of the initial values. So as I said, we have lower temperatures and lower pressures for foaming processes. And one common example, or one example with a big application rate is shoe soles. And we have a partner within the BASF group itself, seated in Lemförde. That's where they develop polyurethane systems, and they also have a Desma shoe molding machine. Who's from the industry will probably know Desma. So it's a fully automatic round table machine where the shoe soles are made and even the entire shoe can be assembled in a fully automatic process. So you have these mold parts that you can see here, left side, right side, and a stamp which moves up and down, closing around last, and then the PU foam is injected into the mold. So again here, by being able to print these molds, you can quickly iterate your prototypes, especially in the early design phase. Again, within 2 to 3 days, shoemakers can have prototypes with the later mass production foam system. It gives them variety and flexibility. They can quickly change designs, swap out the molds on the machine, and have new parts produced. And what goes for the X ceramic 3280 basically applies also for the RG1100 black, but you don't need the thermal treatment. Everything is a bit easier to handle compared to a ceramic filled material. So some things we learned from experience by doing these trials. As we have here very large parts, so really with some really bulky areas, some really heavy and chunky solid material areas. It means a lot of material goes into it, and by hollowing out these molds and filling it, for example, with a gyroid structure, you can save up to 40% material. And not only does this save material, but it also reduces the warpage. Because as I said, it's still a plastic. So having warping plastic, you will see this in any plastics manufacturing technology, and same goes for 3D printing. And the thicker, the higher the wall thickness, the bulkier the material, the more warpage you will see. So hollowing it out and filling it with a structure will reduce this warpage to some extent. We advise to keep at least a 5mm wall thickness to still have a certain strength. And in between the stamp and the outer closing mold halves, we recommend to have a gap of roughly 0.5mm. Or let's say this is a good starting value to make sure that there's no scratching of the stamp against the mold halves. If you are more advanced with the printing process itself, and you know your way around the printing parameters, or you have a good consultant, you can also go down with this gap. We also here we develop material properties to make the materials available in simulation software. So we do a lot of testing, not only the standard quasi-static tensile tests, we test at different strain rates and also at different temperatures. And an example is the little graph you can see down there with the 3 curves of the RG1100 black. The light blue one being at room temperature and the darkest one being at 100 C. So you can clearly see that stiffness and strength go down, but in the same way, the elongation and break goes up. So it gets softer, but it also gets more flexible. It can take more deformation before it breaks. And with this material know-how, we are also able to create material models, or in this case, homogenized material models of gyroid structures, which means we can calculate the behavior of the structure and from this derive a new artificial material which behaves exactly like the structure, and then use it for simulation. Again, machining is a good option if you need high precision and high accuracy. For example, with threads, this can make sense. Or removing the warpage from the down phase, or for ejector pins if needed, printing the holes and then redrilling them to come to the precise dimensions you need are good options. We also tested this material for its machinability, and we give our recommendations in form of these recommended RPMs, which we found work, and this will be further increased in the future with more tools and more testing. But overall, both materials, the X-Ceramic 3280 and also the X-Pro 1100 Black, can be machined quite well. So in the molding process itself, as I said, we used a round table machine made by Desma, located at BASF Polyurethanes. We tested fully solid molds and also the gyroid-filled molds. And the demolding time was roughly 4 and 6 minutes. And the PU foams we tested here were 3 different systems with densities between 300 to 450 grams per liter. The machine itself closes with a clamp force of up to 8 tons. If you keep these recommendations we give of the outer wall thickness and make sure your strength and stiffness stays within a certain range, it's no problem for the molds to take these clamping force. And then on the right, you can see the demolded final midsole, which came out of the process. Some tests on demolding we did. So as I said, we tested 3 different PU foam systems: an Elastopan Sport, Elastopan Safety, and Elastopan Casual. So typical footwear PU systems. And we found basically all release agent have effects, but some do this way better than others. And you can find all of the recommendations and results again online on our processing guideline, including the brand names of the release agents we used. Just giving 2 examples here, the Marbo Super Release S and the Gorapur LS 1040 100B are 2 good examples. So closing up, if this is interesting for you and you want to test this out on yourself, we want to support you. Please pick up contact. So everyone who's innovative and who wants to test 3D printing and combine it with traditional manufacturing methods, like the 2 examples you just saw, feel free to contact us. And with the Rapid TCT coming up in Los Angeles from June 25th to 27th, feel free to stop by and ask our experts to get into contact. If you have ideas to try something out, please come by. And with this, I say thank you for your participation and for your time. And thanks for your attention.
Thanks, Robert. That was really amazing. Appreciate your time. So we have a few questions. If we can get your question today, we'll definitely be reaching out to you and answer those. And there's going to be a recording sent out early next week. So if there's any part in this webinar that you didn't catch, you can review it then. So let's see. There's a ton of questions that came through. Let's do.
Good.
How many parts is possible in PP or PE material in this mold? I'm not sure exactly what mold. I think that was towards the beginning of the presentation, Robert.
Yeah. Yeah, good question. I have to give the boring engineering answer, sorry. It depends. It always depends really on the geometry of the part that you want to make. If you have some really challenging thin ribs or challenging draft angles, which are really steep, it might be that you're only able to make 20, 30, 50 parts. But if you are within a good range of geometric features which demold easily, which are just easy for the process, the injection molding process, I'm sure you can go up to 1,000 or 2,000 parts. Yeah, it's still on our list to really test the limits and see how many parts this material can take. But in one of the examples, I showed you 400 parts, over 400 parts in automatic mode was no problem without visible deterioration of the printed mold insert.
And Ivan has a follow-up question to that. What's the minimum thickness part in this technology?
Does that mean the part to be injection molded, or
Yeah. Mm-hmm.
the printed part? Okay. That's a really good question. To be honest, I don't know it by heart. You will find the results of the different rib thicknesses we tested in our trial with the benchmark tool on our homepage, and it's in the white paper. So yeah, sorry, I don't know it from the top of my head, but you can find the answers there.
Yeah, we can also follow up with that too.
Yeah.
For injection molding, what size backing plates are required? Do you have a yeah?
Not sure what this refers to. Is it about the base mold?
Yeah, let's go with that one. Yeah.
It might be about that one. So the let's say that the maximum printed size of these mold inserts that we still feel comfortable is about 150 by 150 millimeters by, let's say, 50, 60 thickness. And wherever this fits inside is good. There's no hard limit to the backing plates you need or to the surrounding base mold. But make sure that your mold insert is supported on all sides if possible. So also make sure you have a nice fit against the metal frame, the metal base mold surrounding the printed insert.
Great. Let's see. Is there any relation between the chosen resin HDT and the thermoplastic that will be injected? Should there be a minimum temperature difference?
No, really no. So as I said, for plastics which require a lower melting temperature, it just makes it easier, and you can skip the thermal curing step, which is a couple of hours. I mean, the printed mold insert itself, it also has a thermal mass, which will take up some heat. So the mold insert, it does not require internal cooling. Although we have it on our agenda, we will do tests regarding internal cooling, but so far it was enough to just blow the outer surface of the printed mold insert with compressed air, and this way quickly cool it down. Like roughly 20 seconds was always sufficient to cool the mold down enough to take the next shot without becoming too hot.
Great. Let's see. I think we have time for a couple more questions. What infill percentage should you print with, or should it be 100% solid?
Well, I only know infill percentage in context of filament printing.
Mm-hmm.
There you can print parts really hollow. Here in this case, it's a resin.
Mm-hmm.
But if you decide to hollow out or shell your part and fill it with a gyroid structure, yeah, that's a tricky question, because you would need to somehow judge the mechanical performance of this hollowed and structured part now. And for every geometry that you inject plastic into, you have different distribution of pressures and shear forces inside of the cavity. So this is nothing you can answer just like this. But maybe in terms of, let's say, printability, we found to go with a little bit bigger structure and let's say wall thicknesses of these gyroids not below 2 millimeters, because it's a brittle material, and when you break it or when you remove it from the build platform, you don't want to just crush the inner structure because it's so fine. So going on a little more on the bigger and thicker side with let's say roughly 50% remaining solid density should be good to use.
Great. All right, well, we're going to wrap things up here. Again, we're going to send out a recording of this webinar early next week. And if there's any questions we didn't get to, we'll definitely follow up with those. Robert, thank you so much again for your time today. And thank you everyone else for joining us.